We're taking a little digression, not a digression, it's related to what we've been doing, but a little bit more formal introduction to unit testing. Remember that you've got your exam this Friday, asynchronous, take it at your own pace, large window for it. On Wednesday, we'll hold a review, and the way that that will take place is me simply bringing a bunch of old midterms and doing as many exercises as we want to do. So what is unit testing? Well, first of all, what is a unit? Well, a unit is any piece of code that you define to be as a unit. For us, it's usually going to be a function, right? Sometimes it's an entire class, but usually it's a function or a method. If you're in a class-based object-oriented programming language like Java, you could treat the class as the unit, and therefore you would want to be testing that one unit. But the fundamental idea here is that a unit is an indivisible piece of code that is treated as a black box. Right? It's just this thing that we're going to test. For a function, that means giving it inputs, looking at its outputs, and not actually ripping it open and dividing it down further. If you want to do that, that's fine. You can treat snippets of code as units instead. But basically, you want to test things in isolation. And if you're going to isolate something, then you shouldn't be dividing it any further, right? If I've got something that there are two parts to it, and then I want to test this part and this part, well, that's just a different unit, just a different notion of a unit. So a unit is generally, a unit test is an input-output pair that is known to be correct. For example, we're going to write some unit tests here for our AGM that we've been working on, the arithmetic geometric mean. One way that you can generate unit tests, or you test cases, I should say, is by using an external tool, 10 and 20 here. Right? So we'll assume, we'll operate under the assumption that Wolfram Alpha here is correct, right? That it knows what it's doing. And we'll use that as an expectation for our output. So our input is going to be the pair 10 and 20, and our output here is going to be 14.5679 or close enough, right? That's going to be our first unit test case, right? And it's known to be correct or thought to be correct, or you did it on a piece of paper. Or if you've got business rules that this is what should happen in this case, told to you by some marketing person or something like that, then there's your unit test, or that's your test case, right? You're assuming that that's true. Now, they could be wrong, right? And often they are, but it is, at least as far as our tests are concerned, we have to start from somewhere, right? We have to start from some assumption that something is correct, right? Then how do we go about unit testing? We unit test by feeding the input into our unit, that is a function, right? And comparing the result to the known correct or thought to be correct output, right? The expected output. This is the actual versus the expected, right? If they match, guess what? It passes. Right? If they do not match, guess what? It fails, right? Oops, fails, there we go. So if all of our tests pass, then we have some assurance that our test suite is correct, right? Grouping multiple unit tests into one collection gives you a test suite, right? That you can then run over and over and over again. If a future bug is reported, guess what? You have a new test case. Right? So if somebody reports, well, the AGM went haywire when I fed in -5 and 3. Right? Oh, we never thought about that case, right? That was an edge case or whatever. Then we need to go back, incorporate that as a unit test, debug, make sure that that passes, and then we add that to our test suite, right? Future changes that potentially break old test cases that were passing before is known as a regression. So you might have seen this before, regression back to the mean, some statement like that, right? If somebody's high performing, right, they can't sustain that high performance forever, they'll regress back to their average. Likewise, if somebody is low performing, then eventually they're going to get out of their slump and come back up to the average. It's a regression, right? Either way. A regression in testing means that this test case over here was passing. Then we found a new bug that was failing. We went and fixed that bug so that this new bug now is passing. Well, our fix actually broke that thing over there. It was we regressed in our progress, right? And the only way that you can be certain that you have this stuff is by putting it into a test suite and being able to run it over and over and over again repeatably, right? Tests should be repeatable. Tests should be repeatable, right? The more tests you have, the more certainty that you have that your code is correct. However, no amount of tests will ever give you a 100% proof that your code is correct. There's a whole area of research called program validation where you do try to come up with a proof, a mathematical proof that your code is correct. Usually it's niche programming languages, or it's programming languages that support that because they were built to support that idea. It's not actually programming languages that are used in practice. So instead, what we prefer is a high degree of certainty. The more test cases that you have, the more code coverage you have, right? The more test cases you have, the better code coverage you have, right? In other words, what we want to make sure is that that you want to test corner cases. What happens at 0? What happens for negative values? What happens for invalid inputs, et cetera, et cetera? Edge cases, extremal cases, right? Randomized tests. This gets into something called chaos testing, right? Or fuzzing. You try to break your code by feeding it a bunch of randomized values, a bunch of garbage values to try to get it to break, to try to get it to fail somehow. You're trying to fuzz it, right? I don't know where that came from. But in any case, the more test cases you have, the better code coverage you have. If I've got a function that has, say, 5 lines of code, and it has an if-else-if statement, so it has 2 different branches, right? Or it has a loop, like ours does here, right? I want to make sure that every single line of code is tested by at least one test case. Then I have as much code coverage as I have. If I wrote, if there are 5 lines of code, and all the tests that I wrote test only these first 4 lines of code, I am missing out on that 5th line of code that never gets tested. How do I know that it's correct or not? Well, maybe that's a code smell that if you never test it and it never actually gets run, maybe it's dead code and you should get rid of it anyway, right? But otherwise, it means that you have, you don't have enough test code coverage, basically. And there are tools out there that can help you determine that. We're going to look at one today for Java. But you can also have other problems, right? Lack of code, besides a lack of code, lack of code coverage, right? But you can also have another problem called a false positive. That's when a test case is wrong, but the code is correct. So in other words, the test case fails. It's a positive, it fails, but it's false, right? Because our test case was actually badly written. We have a bug in one or the other, right? You can also have like a false negative is when there is a bug in your program, but your tests do not indicate it, right? Because you didn't write it correctly, right? Or maybe there's a false positive because both the code is wrong, the code is wrong and your test case is wrong, but they're wrong in exactly the same way, right? So 2 wrongs in this case ends up making a right because it ends up passing, but it's another false positive, right? Generally, you can follow what's called TDD, which is test-driven development. Now, there are some pedantics out there that claim that this should be the way of doing things. No, There should never be any hard and fast rules about anything because there are always exceptions to those rules. But the idea here is that you write tests before you even write the code. Right? There's no real problem in doing that, but you can go ahead and write it in parallel. You can go ahead and write it afterwards, right? Test-driven development says that you should always do it beforehand, right? Otherwise it shouldn't be an afterthought. Definitely it should not be an afterthought, but being pedantic like this, writing your test before you even write the code, no. But sometimes the code helps you to formulate tests. Sometimes the tests help you formulate the code, right? So it should be this, I like to think of it as the Escher painting, the Escher hand painting. Escher hand painting. All right, it's not a painting, but it's a drawing. All right? One hand drawing the other. Okay, there we go. That's the one. All right? So the tests inform the code informs the tests, and it's this endless feedback loop where both of them are done in parallel, both of them are done as companions, right? We've all seen this probably, you just didn't know. Maybe it was from MC Escher. Yes, no? No, you never seen this before? No? Okay. It's kind of, all right, fine. It's kind of cool, but whatever. All right. So that's how I like to think about it, at least, right? That you can come up with that code beforehand, but whatever. Right? So what we're going to do today as a demonstration, and eventually you'll do it anyway as part of your hacks, but for our demo here, we'll do an informal unit testing in C, and then we'll do some formal unit testing in Java. And for that, I need to start my Eclipse because it's going to take maybe a minute here, but once it's gone, good. Okay, so we'll start it in C over here. So here's my unit, right? Here is my AGM function, right? I've got, I did some ad hoc testing, right? When we ran it through that demo.c file, I just, ran it and said, okay, that looks good. And I compared it with the result over here. Yeah, that looks good. That was just ad hoc. That's not repeatable, right? If I wanted to do that over again, I would have to go back. Remember, I deleted it all so that we could do something else, right? I would have to go back and rewrite all that testing code. What we're going to do now is we're going to be a little bit more formal, and we're going to write our own unit tests over here, right? So let's go ahead and where's the test? There we go. My math test, right? And that's just what I named it. So in my main here, what we're going to do is we're going to write some code to automate this. For example, my first test case here will be my inputs will be, say, what did I do over there? 10 and 20. 10 double y is equal to 20, right? And double expected output should be, what was it? This thing right here. I'm not going to grab all of it. I'll just grab a part of it because, of course, it's doubles are only accurate out to 17 decimals anyway, digits of accuracy. And I'll go ahead and leave it like that, okay? And then I need the actual output of my function. To do that, I now need to actually call my function, AGM of x and y. Now, I've got my input, I've got my expected output. That's my test case right there. Actually testing it would be grabbing that output and comparing it. If expected output is equal to actual output, then that means I got the same answer. So what should I do? Printf passed. There we go. Otherwise, if they're not the same, what should I output? Failed. Those two words are really nice because they are both 6 letters. They line up nicely with monotype font, right? So I could also put out some sort of a message here, printf, testing AGM of %f, dot, 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 right? Not going to the next line, right? And then it'll actually output, passed or failed, depending on that, right? But I could also, if it failed, I could actually give some more information here, right? Failed. Expected %f got %f. In other words, expected output here. I'll report the expected output and the actual output so that if it fails, you can go off and explore it further and debug it and you know see what was wrong, basically. Okay. Well, one test case is not enough. Let's go back over here and make another test case. Give me your favorite numbers. 42. Okay, good. Douglas Adams out there? Yeah. 0? Okay. There's an edge case. All right. What should the result be? 0. All right, well then, cut and paste this entire thing for the second test case. All right. 42 and 0. What's the expected output? 0. And then I'm testing those two things again. If it's equal, then it passed. Otherwise, if it fails, it outputs this stuff. Right? Except that now I have 2 test cases. Is this going to compile since I've redeclared everything? Nope. Get rid of that. Get rid of that. Get rid of that. Get rid of that. And in fact, what I would end up doing is going up here and declaring all these separately. Double X, Y, expected output, actual output, and be done with it. So that I don't have to declare them here, declare them here, declare them here, declare them here. There we go. Okay. But now that I have 2 test cases, maybe I want a summary report at the end, right? Maybe I want to know how many test cases failed and how many passed. Num passed, right? And I'll initialize that to 0. Int num failed, and I'll initialize that to 0. So that every time I pass, num passed, plus plus, and every time I fail, I increment the other counter, num failed, plus plus. Right. Same thing down here. Num passed, plus plus, and num failed, plus plus. So that down here at the end, I can give a summary report, right? I can say printf %d passed, right? And the line num passed. I can report the number failed. Failed. Right? And I can even report, say, a percentage. Printf percentage percent f 2f, let's say, percent passed. Right? And line. Now, how do I get my percentage? The num passed divided by the num passed plus the num failed. Right? The total number of test cases. Okay. Is this going to work? Predict. Integer divided by an integer plus an integer. What is that? That's an integer. How do I make this not an integer? Typecast at least one of those things. Also, what scale is this going to be on? What is 50%? 0.5? Right? If I print it out as a percentage, what should it be? 50.0? So what can I do? Times 100. All right. Refresh my memory. How do we compile all of this together? Can I just go GCC my math test and be done with it? Nope. First of all, I've got some errors here. There we go. Is that it? Yep. Okay. Everything's saved. Nope. What is AGM? I don't know anything about AGM. Well, I included my math.h. It doesn't know anything about square root either, right? What do you do to bring in the math library when you actually compile? -lm, right, to link in the math library. I need to link in my math library now. How did we do that before on Friday? We compiled, right, it's in the notes. We compiled, where is it? Up here. mymath, which produced a mymath.o file. And then if we wanted to actually compile the demo, or in this case the test, then we bring in the .o file just like we would with -lm. So gcc c mymath test.c, or not test, sorry, .c. That produces a mymath.o file, which was probably already there. And then I could go ahead and compile them all together with mymathtest.c, mymath.o, the library, and also -lm to bring in the math library. That produces an a.out file that I can then run. 2 failed. All right, I'm glad that I'm testing. What's wrong? First one looks like it's passing, right? It expected that number, it got that number. What are you complaining about? The hint is in the second one. Expected 0, but I got 0.000005. Right? Remember, how does our function actually work? There's a tolerance built in there, right? That when it converges and it gets close enough, then we stop and report that result. One way that we could fix this is by saying, all right, more significant figs, more sig figs. Right? And recompile the math library, recompile the whole library there, run it again, see if it passes. Okay, still not close enough. Why? How close were my tests? They went out really, really far, right? So either I'm going to have to change it so that it's really, really accurate, which I don't want to because this is accurate enough. I need to go to my tests and modify my tests to conform to my expectations. You don't need to be accurate all the way out that far, right? In fact, you can't, right? With floating point numbers, equals will probably never work. We need to build in a little bit of tolerance here, right? So double tolerance is equal to 0.00001, right? Let's say. I'm just pulling that out of the air here. And now we no longer check for equality here. What do we check for? If the difference between these two things is small, right? The absolute value between these two things is small, is less than our tolerance, then we say that it passes. Right? It's close enough. So when you're doing tests and you need to build in a little bit of tolerance, then fine. Don't go for strict equality. If you were working with integers here and you had a function that output an integer, absolutely go for equality. If you expect 5 to be output, 6 is probably, 4 is probably not tolerable, right? No, that's wrong. It should be 5 here. Right? So we'll go ahead and build in a tolerance here. And then a note here, I put it into a variable so that I can change that and tune it if I want to. But otherwise, there we go. And then I have to recompile everything. I have to compile that thing. I have to compile that thing. Oops. What did I do? Too many parentheses. Is that right? Too many parentheses. There we go. All right, compile that thing, and now that I'm using fabs, what else do I need? Include the math library. There we go. Fine. There we go. Now that was only 2 commands, but imagine if I had, dozens and dozens of files and different tests and maybe 100 different test suites. What tool should I use for repeatable builds like this? What did we look at on Friday? Didn't we look at make files? I thought we did, didn't we? No? Okay. We've got time. Let's digress. Hopefully GitHub is a little bit better now. You'll see this eventually in your labs next week. But if the code base gets too big, right, then the rules for building stuff are going to be too complicated. And so what you can do is you can write in another language rules for building stuff. For example, here in your lab 5 next week, there are not a lot of files. There may be like a half a dozen source files here. But even that is, that's too much. I don't want to have to type every single time I want to compile something. So we provided what's called a makefile. And this is for any programming language, but it's another programming language that specifies rules for building stuff. It's a programming language because it has variables. Right? What's your compiler? My compiler is GCC with this flag standard here. What flags do you want to send into your compiler? Well, I want to turn on all warnings. What includes do you want to include in your compile? Right? The -lm flag in order to bring in the math library. There are several rules here. A rule takes the form of the following. In order to build this thing, : It depends on these things over here. Next line, tab over. This is the rule for building that thing. Right? And here is where my variables come in. Right? So that if, I'm using the same thing over and over and over again, so that if I wanted to change the compiler that I'm using from GCC to, I don't know, Clang or something else entirely, then I can go ahead and do that with just one change. Right? But let's look at image driver here. Image driver depends on these three things. It depends on the image utils, the color utils.o, and the image driver.c. Well, okay, image utils.o, how do I build that thing? There's another rule for it. It depends on these two things, and this is how you end up building it. Right? So this is only for maybe 8 source files, half a dozen source files, and I've got 4 rules for building stuff here. I've got a rule for building my tester. Let's go ahead and use this. In fact, I'm going to just go ahead and steal this code right here. And let's create all of it right there. And let's go ahead and create our own makefile. Right? So touch makefile. Right? Refresh this. And where's that makefile? There it is. It's makefile without a .txt extension or whatever. Right? There we go. We're not going to create an image driver here. Instead, we're going to create what my math test suite, like say, and it depends on what? It depends on my math test.c and my math.o. How did I end up building these things? I used GCC with my flags, my includes, my math test.c, and I brought in my math.o. And that -lm is being taken care of by those includes. And my output file here is going to be my math test suite. There we go. Am I done? Did I specify how my math.o gets built? Nope. So put in that rule. It depends on my math.h and my math.c. And same thing as up here. And this is a tab, right? Yep. It does require a tab. You can't just go space, space, space. That's part of the language. Right? This is an entire other computer programming language here. And to do this, I go my GCC my math.c, and my output file will end up being my math.o. There we go. Now, instead of having to repeat these over and over and over again, all I have to do is go make it for me, and it's done. Right? Darn it. My math test, I call it my math test, right? My math test, my math test, my math test suite. Okay. Why are you complaining? Oh, I know. Duh. How do we compile something without actually creating an executable file? -c. Right. I forgot my -c there. Right. There we go. Make. Done. Right. No news is good news. Now look over here and you see that there's this new program over here called my math test suite. I can run it, my math test suite. Hey, now everything passes. And now I've got an entire framework that if I want to go back and create more test cases, what do I need to do? Copy, paste, copy, paste, copy, paste. I wonder if there's a better way than copy pasting this entire block of code here. Copy, paste, copy, paste. Should we do that? Nope. Instead, what could I do? I could make a function to test my functions and then use that function over and over and over again. Right? Now, this is an informal test suite, right? We wrote everything from scratch here in about a half hour, right? That's not usually how you do it. Instead, what you usually do is you use a unit testing library. Right? And eventually, not next week, but the week after that, you'll take a look at CMACA for C. It's a unit testing framework for C. It's not the only one. There are dozens out there, but it's the one that I'm using for this course. Right? What does it look like? You can go ahead and read, hours and hours of documentation if you want. Otherwise, we give you a test file as an example, document it fully to show you what it looks like, and then you just have to extend it by adding 1 or 2, like 3 test cases on your own for each of the functions that you implement. So you don't reinvent the wheel, right? That's the whole reason to use functions. That's the whole reason to use libraries, right? We're not going to, this is what you do on, I think, Lab 5 and maybe even Hack 5. But ultimately in the real life, you use a library to do this kind of stuff. Right? So what does it look like in Java? There's my AGM, remember? My math. And I've got this epsilon tolerance here, right? I'm not even going to bother going through the informal way of doing this, because seriously, all it would be a cut and paste, change printfs to system.out.printf, change fabs to math.abs. There would be no changes here at all. Right? Instead, I'm going to jump right to the formal test framework, which is called JUnit. JUnit. And we're on version 5. You should not use anything older than that. And so, again, hours and hours and hours of documentation if you want to. Otherwise, you can just jump into it immediately by the example that we give you. There are some instructions for how to install it in Eclipse. It's really easy. You right-click your project, build path, add libraries. And one of those libraries, guess what, is JUnit. You're done. I already did this. My math tests, let's take a look at how I did this. So I imported a bunch of stuff from the unit testing framework, org.junit.jupyter, org.junit.assert, assert equals. And here's my first test, test 001. I think this is the value that we had before, right, last week. And the value that gave you that was 42 and 101. So I've got an expected value, actual value. I didn't bother putting these into variables. I just put them directly as calls to that function, my math.agm. And I assert equals. I assert that the expected and the actual are equal within a tolerance of epsilon. And if they're not equal, then this message is output. Right? Now, unlike my math test over here, where I was doing everything in a main, do you see a main here? Nope. Magic. You can still hit the play button. This is called, it's all done through reflection, which is aspect-oriented programming, which I kind of ignored. How did this work? How did you know that this was a test other than the name test? I could have named this anything I want. Some function here, right? How did you know that it was a test? How did Java know that it was a test? This thing right here. That's called an annotation, right? It is not actual code. What it is it's an aspect. It's saying, hey, Java, this function right here, it's a test, right? So treat it as a test. And what it does is it goes out and injects code, right? It modifies your code by injecting code around it or adding code that ends up calling this function without you having to worry about it at all. Right? There are lots of these annotations. Right? They're all in the API, Application Programmer Interface. I'm only going to show you one today because it gets the job done. Right? Here is my test 001. It passed, all green right here. Nice, right? But now let's suppose that I have a bad value, 42. What does a failure look like? Run this. Red. I don't know, that's more like a scarlet. Is it? How does it appear up there? It's supposed to be bright red, but in any case, it's giving you a message here. Not close enough. I expected 42, it's kind of hard to read down here. I expected 42, but it was 68.27. Right? Did I write that code anywhere? Nope. It was all taken care of for me by the unit testing framework. CMACA would do something like this as well. All right, so let's reset that. Give me another test. Can't call it 001. I can call it 002. Right? What were the values that we were playing around with before? There's that thing, 10 and 20. 10, 20, there we go. run that. It all passes, right? And I even get a nice summary here. 2 of 2 passed, or 2 of 2 were run, 0 errors, 0 failures, all green. Right? What if I wanted another test? Copy, paste, third test, and what did you say? 0 and what? 42 and 0. There we go. Hit the play button again. Right? And it finds 3 of 3, and they're all passing. Nice, right? A good, nice formal unit testing framework will save you from having to write all of this basic stuff here, right? That we did. We only wasted a half an hour, but imagine wasting a half hour every time you want to test something, right? That adds up. So using a formal unit testing framework here is better. And in fact, what I can do is I can go back and say, I don't know, change my epsilon here. I want more accurate. I want more significant figures here. Do I have to ad hoc test everything over and over and over again? No. I click one button, good, ship it. Right? Unit testing is usually integrated into what's called CI, which is continuous integration, where you write your code, you run your tests, you check your code in as a commit, you push it out to a more formal testing environment or something like that, and then eventually it becomes part of the production code. Right? This is a continuous integration process that every time you make a change, in the background, say, all the tests are being run over and over again. Just like over here, if I make a change, the compiler is trying to compile in the background with every keystroke. Continuous integration can do that, but also for testing. Right? Nope, you just screwed up. You added a piece of code, a line of code, that now none of the tests, or that 5 of the tests are failing. We're not even going to let you commit that code. Right? There are some organizations that have strict rules against even that. Right? We will not accept any buggy code into the repository at all. Right? And so you have to go back, you have to fix it before you can even commit it. Right? To Git or GitHub or whatever you're using. Questions on that so far? No? Okay, so we're not going to require, other than the directions in Labs 5, 6, and Hacks 5 and 6. After that, we're not going to require that you use one of these frameworks. You should just get into the habit of using it. Now, for something as simple as AGM, you're done, right? For something as simple as, say, round to sense, you don't need a full testing framework for that. All right, but for bigger things, you'll want to get into the habit of actually, implementing full test suites. It's how the grader works. The grader is an informal unit testing framework where we have input, expected output that we've developed because we have another solution, right? And then we run yours against that, and if it matches, it's great. Right? Later on, there are even entire suites where we run, say, 1 million randomized test cases, right? And then it reports you failed 500,000 of them, right? Or something. And it just reports a summary of 100% or 75% or something. All right. Any questions on the exam this week or the resubmission? No? All right. Generally, after the first exam, what I do is a grade checkpoint. I don't think there's that much for this class, but I also invite at the same time for any feedback on how the course has been going so far, the pace of the course. I get the sense that at least for the honor section here, that the pace is good or maybe too slow. Don't worry, we'll ramp it up as we go along here. If it is too fast, then and I'm saying that we're going to ramp it up even further, then let me know that. Let me know if that's your feeling as well. But otherwise, there will be a post on Piazza after we've gone through the first pass of grading for the first exam. The best way to prepare for the first exam is to just go through your past stuff. If you've done well on all of the hacks, you're good to go. Don't worry about it. Right? Yeah. Well, if you want a lab reconsidered, you go to the lab, right? If all your labs are 100%, you don't have to go. I mean, if you want to go and just hang out or work on something else or whatever, that's up to you. But the LAs will be in the lab. Yeah.
I may have missed or something, but for the exam, is it through the DLC or?
No, it's all the details are on Piazza. Go through that again really quick here. 155H. You can find it really quick by going to this week's post, and then I backlink to it, right? So this Friday, it opens up at 9 on Canvas. That's already been set up. It'll have several programming exercises, actually 2. So I'll let you know how that works for this course, because you'll have 2 exercises. You have to do 1 in Java, 1 in C. The choice is yours, right? The grader will accept either one, but don't do 4 programs. The 2 exercises in C, 2 exercises in Java, and then hand them all in, right? Then the grader won't be able to detect that. Then I think it has a preference for the C versions. But in any case, it's open book, open note, required computer, because you will be writing these programs, submitting them to the web hand-in, using the web grader to check them, etc. You have until that midnight, well, 1 minute before midnight, that Friday, after which no further consideration will be given. So you're given, what, 15 hours? It's only going to take you 1 at most, right? Otherwise, again, the emphasis here is that do not consult with anybody else. Trust me, if you have to consult on these programs that we're giving you in this first exam, you're lost. You might want to start over on a different course, right? But otherwise, the School of Computing does take academic dishonesty very seriously. We have a 3 strikes and you're out policy, 3 documented plagiarism cases, and you're out of the major, any of the 3 majors. Right? So please don't even consider it. Right? And it's stupid easy to detect it using our MOS system, measure of software similarity. Right? Discuss the exam all you want after midnight on Friday, but not before that. Any questions? All right, then Wednesday will be a review.